Hello, this is Mrs. Myers. We are going to be proving some of our parallel and perpendicular line proofs. Some of these theorems, I should say, we're going to be proving them using our two-column proofs. And there are going to be 3 new theorems. We've learned a lot of theorems with just parallel lines. Now we're going to be including perpendicular lines and how they relate to parallel lines. Remember, perpendicular means two things that intersect to form right angles, and parallel are two lines that never intersect but are in the same plane. Okay, so the first one we're actually going to call the transitive property of parallel lines. Remember, we've learned the transitive property of equality, like if A equals B and B equals C, then A must equal C. First equals last, right? And that was a property of equality and of congruence. Well, now we're saying if line D is parallel to E and line E is parallel to F, well then line D must be parallel to F as well. Okay, so if the first line is parallel to the second one and the second one's parallel to the third one, then the first one must be parallel to the third one. It kind of has that transitive property feel to it. Remember, this is not equality or congruence this time, it is just parallel. Okay, so we're going to start by saying our given. If B is parallel to E and E is parallel to F. Okay, well, if D is parallel to E, based on the angles that are numbered here, we can see that 1 and 2 are corresponding angles. So if D is parallel to E, then 1 and 2 must be congruent based on the fact that they are corresponding angles. So that is the corresponding angles theorem. All right. Then we have this other fact given to us. E is parallel to F. Well, the angles that are touching E and F are 2 and 3, and they are also corresponding angles. So we're going to say angle 2 is congruent to angle 3, again by the corresponding angles theorem. Well, if 1 is congruent to 2 and 2 is congruent to 3, then 1 must be congruent to 3. Angle 1 congruent to angle 3. Remember, this has that link. It's linked by the 2. It's like the zigzag. 1 is congruent to 2. Boom. 2 is congruent to 3. Therefore, first is congruent to last. That is the transitive property of congruence. All right, well, if 1 is congruent to 3, well then D must be parallel to F, right? If we completely don't look at that middle line, if we ignore that for a minute and we just look at D and F, if 3 and 1 are congruent, then D and F must be parallel. Remember, whenever we're proving lines parallel, we're going to use the converse of one of the theorems. And again, 1 and 3 are corresponding angles, so it's the converse of the corresponding angles theorem. Okay, so now we've proven this, and we can call it the transitive property of parallel lines. So now, from now on, since we've already proven it, when you're in a proof and you have this situation where 2 lines are parallel to a third line, then those 2 lines are parallel to each other. Okay, so you can just jump straight from 1 to 5 in a future proof just by using transitive property of parallel lines. Okay, so see that. The next theorem. In a plane, if 2 lines are perpendicular to the same line, then those two lines are parallel to each other. Well, let's think about this. If two lines are perpendicular to the same line. So in this diagram, the two lines are N and O. They are both perpendicular to T. So our given is T is perpendicular to N, and T is also perpendicular to O. So two lines are N and O, they're both perpendicular to T, then N and O must be parallel to each other. Okay, how are we going to prove this? Well, look at what we have numbered here. Angle 1 and angle 2. What kind of angles are they again? Well, these are corresponding angles. If both of these are perpendicular situations, then both of these corresponding angles must be right angles. If they're both right angles, then that means they're congruent. And if they're congruent, then the lines must be parallel by the converse of the corresponding angles theorem. So again, we're going to start with our given. This time I'm going to break up our given just to show you how to break up the given and use each given for what you can. So in this case, I'm going to use the fact that T is perpendicular to N. T is perpendicular to N. So therefore, I can talk about angle 1. Because angle 1 has to do with, or angle 1 is formed by T and N. So angle 1, I'm going to say angle 1 is a right angle. Because when we look up the definition of perpendicular, it says two lines that form right angles. So if T is perpendicular to N, then by definition, we can say they form right angles. Angle 1 is a right angle. Okay, now I'm going to move to my next given. T is perpendicular to O. Well, that's my next given. Well, based on that given, I could say angle 2 is a right angle. Again, definition, perpendicular. I hope you're thinking this through with me, not just copying down what I'm saying, but think it through with me. Okay, so they're both right angles. Well, if they're both right angles and I'm trying to get N parallel to O, I want to be able to say these two angles are congruent and therefore lines are parallel by converse of corresponding. So am I ready to say angle 1 is congruent to angle 2? I am ready to say this because they're both right angles and we learned the right angles theorem. The right angles theorem said all right angles are congruent, or if two angles are right angles, then they are congruent. So the right angles theorem allows me to say if I have two right angles, they're congruent to each other. All right, so now I'm ready for my last step. N is parallel to O, because if 1 and 2 are congruent and their corresponding angles, I can say that the lines are parallel by the converse of the corresponding angles theorem. Okay, so again, now that we've proven this theorem, we just proved the theorem, anytime you have a situation where two lines are both perpendicular to the same line, you can go straight to saying those lines are parallel without writing all these steps in between, because this was the proof of the theorem, right? So you could go straight to saying this is true using this proof. And now, this theorem. Now this theorem doesn't have a name, so we would just have to spell it out. We would have to just say, if two lines are perpendicular to the same line, then those two lines are parallel to each other. You would have to just write that out. If two lines perpendicular to same line, right? So in a proof in the future, right, we couldn't use that here because we were proving the theorem. But in a proof in the future, you would have to just spell that one out. Okay. The last theorem we're going to look at here is the perpendicular transversal theorem, which basically says if a line is perpendicular to one of two parallel lines, then it's also perpendicular to the other line. So you're given here that these lines are parallel. We know the lines are parallel. Then you're given that this third line, A, is perpendicular to one of the lines. And you're trying to say then, oh, well, if it's perpendicular to one of the parallel lines, it has to be perpendicular to the other parallel line. That's what we're trying to show here. Given parallel lines and one thing known to be perpendicular, you're proving that the other thing is also perpendicular. A little different than what we did before. What we knew before in this one, what we knew two perpendicular situations, and we were trying to prove lines parallel. Now we're given lines parallel and one perpendicular situation, we're trying to prove the other one perpendicular. Okay, so we are given A is perpendicular to B, and we're given that B is parallel to C. So we're just given this one perpendicular situation. We're trying to prove A perpendicular to C. So A perpendicular to B. I'm going to break up the givens again. Think of your givens as like wet washcloths. Washcloths that are full of information, right? We want to squeeze as much information as we can out of each piece of given information. They don't give us random information that we're not going to use. In most cases, every piece of given information is going to be used. You got to figure out how you need to use it. So based on A is perpendicular to B, the information I'm going to squeeze out of that is that angle 1 is a right angle. Think now. What's the reason? If A is perpendicular to B, angle 1 is a right angle by definition of perpendicular. All right, that's the first given. Not much else I can say about that. I could say it's 90 degrees, but I don't think I'm going to need to. I'm going to just leave it at being a right angle. Okay, the next given is that B is parallel to C. What information can I squeeze out of that one? Well, if B is parallel to C, what do we know about these two angles? Well, I can say angle 1 is congruent to angle 2. Reason? Because they're corresponding angles, so it's the corresponding angles theorem. This time it's not the converse, right? We know the lines are parallel, so we're saying the angles are congruent. That's just the corresponding angles theorem. Now, I want to be able to say that A is perpendicular to C. So what I want to be able to do is say that this is also a right angle. So if I want to say this is also a right angle, I really can't go to that right now yet. So it looks like I am going to need some substitution in here. I know that this is a right angle, so it's 90 degrees. I know that these are congruent. So I know in my head that this has to be 90 degrees. I don't have a justification for going straight to saying it's a right angle right now, so I'm going to have to use substitution. Well, if I need substitution, then I'm going to have to use angle measures. Not congruence, not right angles, but actual measures of angles. So I'm going to say measure of angle 1 is equal to the measure of angle 2 by definition of congruent, right? Because if 1 is congruent to 2, then 1 is equal to 2 by definition of congruent. And I am going to say that the measure of angle 1 equals 90 degrees. Why? Well, based on my statement 2, angle 1 is a right angle, so the measure of angle 1 equals 90 degrees by definition of right angle. I know what a right angle is. A right angle is a measure of 90 degrees, so that's just the definition. So what I'm going to do now is I'm going to take this and rewrite it, keeping in the measure of angle 2, kicking out the measure of angle 1 and replacing it with a 90. That's going to be my substitution. Remember, substitution has to be substituting into an actual equation something that you've stated as being equal to each other. Well, if angle 2 equals 90 degrees, then I can say angle 2 is a right angle. Right angle because of the definition of right angle. Definition of right angle, right? Because I knew it was 90, so I said, oh, that makes it a right angle. That's because I know what a right angle is, not anything else. Now I'm going to say A is perpendicular to C. Why? Because if angle 2 is a right angle, then since I know that the definition of perpendicular means two things that come together to form right angles, once I know angle 2 is a right angle, then I can say the lines are perpendicular. And that's our proof. Again, we've proven the theorem, perpendicular transversal theorem. Now, once we know all this given in a future proof, you could go straight to this statement based on the theorem itself without going through all the steps. Okay, there's some exercises here. I would like you to actually complete these exercises based on what we just learned about if two things are parallel and one is perpendicular, well then the other one has to be perpendicular. Or if two things are parallel and both parallel to a third line, then they have to be parallel to each other. And if you know things are parallel and one perpendicular, then they have to be, or two, I should say, if you know two things are perpendicular, then these two would have to be parallel, that kind of thing. So that should help you solve some of these problems here. And there is one proof. I would like you to do those, and we'll talk about them in class tomorrow. Okay, thank you.